So, I will hopefully finish out the software and security course, and then Adam can pick back up, or the market courses, and Adam can pick back up next time if he manages to recover from his ordeal. No, he's just not. Did he get arrested? No, he's okay. He's not maimed. I can guarantee you that last time I saw him, he was not maimed. Much could happen in a little short amount of time. So who knows? Okay. Anyways, I'm Yan Shoshitaishvili. I'm an assistant professor here at ASU with a study focus on binary security, which is, a research focus rather than binary security, which is what we are going to talk about. So hopefully I won't embarrass myself too much because this is what I do. So, as I understand it, last time, Adam took you guys through buffer overflows, and then he mentioned, hey, what happens if the stack is not executable? And of course, the point of a buffer overflow, you have the stack, and by the way, Adam draws the stack vertically with the high values on top, low values on the bottom, and as things get pushed onto the stack, it goes down. This is correct, Adam. This is a stupid way of drawing the stack. Don't tell that. Well, actually, tell Adam I said it, but he's wrong.
You're one of those people that draws the
In my opinion, the stack should grow sideways. We read sideways. Why not have the stack grow sideways? It makes sense that things to the right are bigger. When you write stuff, it makes sense. If you write to the right, But okay, Adam does it this way, so he'll stick with this. And from here on out, I blame every mistake I made through the rest of the class on this whole improper thing here. Well, also that won't erase. Anyways, so the traditional kind of buffer overflow, right, that you have, you guys went over how you might have a function, right, and it's like whatever, in something or a lot, and here it does a return. And the way this works is when the function gets called, it saves a return address onto the stack. There's a bunch of other crap on the stack. The save base pointer, et cetera, the local variables. And eventually when the function returns, it just reads this address and it jumps there, right? The idea being, if you have int foo calling int bar, then the return address will point right here after foo. When bar returns, it'll read that, jump there, and execution resumes, right? This is nothing new. Of course, you covered buffer flows. If you override this with something evil, and then also put some shellcode on the stack, you override that with the address of your shellcode. That's the classical buffer overflow exploit. And then people came out and said, hey, here's an easy way to prevent this. No one should really be executing code on the stack. The stack's for data, so let's have a non-executable stack. Right? That's kind of nice. I covered this last time. Hackers responded to this, said, screw that. We're going to, this is all about an X. And so, all about an X. Hackers said, you know what? Let's invent something called return into libc. And the idea is we don't need this code. Screw that. We don't need shellcode. What we have is somewhere in libc there is something, a function called system, who here has used this function to call out to shell commands. Yeah, awesome. And we just point this to system and then put some arguments over here, so that system then reads these arguments and, oh, okay, I've been, I'm a libc function that has been legitimately called by some messed up code, and it just runs it, right? So we've now avoided this NX. So this was all last time, right? And we can run through how this would look like with our vulnerable program. And I will go through this right now because we'll be using the same vulnerable program in today's lecture beyond return to libc. But basically, what this program does is first it pushes the base pointer onto the stack, saves the current base pointer. It creates a new base pointer by moving the stack pointer into EBP, and everyone here is familiar with the base pointer, right? This is nothing new. It makes room on the stack, so you have to do this super awkward thing where for some reason you go down instead of up, or instead of to the right, and so there's a return address from the, hold on, that's dead. Someone remind me, that looks like, close enough to trash. All right, there's a return address on the stack here, and then it pushed the saved frame pointer, and then it makes some room for its local variables. And then it sets up this call to stir copy. Does this work? Is it visible? All right, or, okay, that's not visible, interesting. All right, anyways, so it sets up the call for to stir copy. Why did we do that? Right, okay, so it let's see. Did I have to tell you guys about AT&T versus Intel assembly syntax?
Yes.
Yeah, so AT&T syntax is not used by anyone in their right minds. So that's going to be my excuse. And so I have to constantly like, okay, we write EAS, no, we don't write it. We read from EBP plus OXC. Okay, this is, yes, okay, good. So this is, right, I see. We are getting argv1, right? And then eventually you're loading where it's going to go, minus OX32, which is 50. So it's this foo variable, offset OX32 from the base pointer, and then we call stir copy, which of course wrecks our overflows our buffer, wrecks our return address, we move 10 to EAX, and we remount the stack and return. Of course, as mentioned, you have to disable a whole lot of security protections to get this example working. But what this creates an out file that has a bunch of segments. You talked about this last time, right? Some of these segments are executable, some are not. And if we run, look at that as a system, so here's where system is in our loaded program image. If we actually look at where that's mapped, you can see system, you can see that libc is mapped over here at B7E25000, and system is populated at B7E66310. So we actually map in this one, right? B7E, yeah. And this is a readable and executable segment of code, and this makes sense. So then we try to find somewhere in libc that has the string binsh. We found it, it's somewhere in libc. as expected, and you can put that out. And so what you want to do is call system with the string, which is in there, with the string bin.sh, which is here, right? And this is the return into libc exploit.
I have a quick question. In GDB, how can you find the process ID in there? Or is that, you have to do that ID? That's just a quick question.
This info inferior, or
Oh, it's the process
yeah.
ID for, okay.
Yeah. Also, what you can do, there's a command pgrep you can execute from outside of GDB, or you can just look at the process table, look it up, or /proc/self/maps. When you're right now, you'd actually do that in the context of GDB, and it wouldn't be useful because it's not GDB that you're interested in. It's the process you're analyzing. But if you want to know your shells mapping, for example, to play around with that, or whatever other process that you have exploited that you're trying to understand where stuff is in memory for some next stage exploit, you can use /proc/self. It's a symlink to the correct process ID. Cool. So the exploit is basically this: we print 50 A's, and then we print some crap to overflow the say base address, and then we print the address of this should be the address of system, and then we print the argument to system, which is the address of bin.sh, or print. Yeah, you're printing it in Python, but then it's all given as an input to the program in GDB. So then we start running. Here's our string copy. Boom, we overflowed the buffer, messed it up pretty good. So this is our 50 A's. All right, here is BCDE. This is just some crap that we wrote over the base address. And then here is the system address, and here is the bin.sh address. So then we start executing, we do a leave, boom, we pop that off, pop off this address here. We do a ret, it returns into system here, and now this is the top of the stack, pushes the and then system runs, right? So we're not going to go through system evidently, but then system runs, and system will actually execute itself with argument bin.sh. This all makes sense. This is from last time. Cool. Okay, so then let's move forward. We can see what runs here, and then this complains because we have a new process running in bin.sh. Wait, no, we don't.
I think it's a stack.
Yeah, the stack got fucked up, so then we stack. You're right. So, why did the stack get fucked up? The stack got messed up because we forgot about system expects a return address to be the next thing. And so when we put our bin.sh right after the address of system, then system can't, when system looks at the argument, it looks at this BFFF in the argument, and it's no good. So we do it right. Oh, yeah, there. We do it right, and we actually pad another fake bunch of data before we put our argument. This fake bunch of data, this works, of course. Why does it work? It works because when system gets run, it sees this as the return address to return from system, and then it sees this as the address of the first argument. And so then it works. So this allows us to do something interesting, right? Which is called function chaining. Instead of that fake EBCD, we can put the address of any other function, and system will return to it when it returns. And we can make arbitrarily long chains of this to execute libc function after libc function and do whatever we want. We now don't need shellcode, right? We can just program this stack in some sense, like you would program a normal application using C. Now, grabbing the return values of things is a little tricky, but realistically speaking, if you can execute library calls, then you pretty much won as an attacker. Of course, we have to think about how the stack looks and all that, but things are pretty good. This is like Christmas time, right? And so attackers quickly moved on to returning to libc, and of course, defenders said, "Oh no, you don't," and they came up with something to counter that, called address space layout randomization. The idea here is pretty simple, right? Returning to libc is possible because you can tell where system is. The first step of that exploit was, hey, let's print out the address of system. Okay? And if system's always in the same spot, then of course that's trivial. You print it out locally, or you just have a very similar environment to your remote victim, figure out where system is on your environment, attack, boom, you win. So the idea is, let's make that no longer true. Let's put system, or hell, let's put all library code, or while we're at it, we can also do the stack and so forth and so on in some random area every time where you can't predict its location. And this is actually already possible because the way that libraries are written, a program can have a link against multiple libraries at the same time, any combination of libraries, right? And so when you have a memory space going from, these don't do very well. If you have a memory space going from left to right, you have your program somewhere in memory here. That program was at 800 something earlier, right? This is the program. You got your stack going backwards, all good. You have your library somewhere, right? Let's say program A uses libc, libmath, and libgl, right? So you'll put libc, libmath, and libgl. Another program might just use libc and libgl. So, libc, libgl. Now libgl is in two different places. Right? You might say, okay, well, we can say, all right, always load libgl at a given offset, and then you're okay. If something doesn't use libmath, then it just stays empty. That doesn't quite work either, because programs, you can't just assign these locations to a library. That takes a lot of coordination that no one has. You will eventually have a program that uses two libraries that all expect to be loaded at the same address, right? So as a result, libraries are written to be position independent. Right? A library expects to be loaded somewhere and to execute, and that somewhere, generally the original intent is that somewhere that is loaded is at one of these slots. And libm can be loaded in this slot and it's perfectly happy, or it can be loaded in somewhere else in memory and it's perfectly happy to support many different programs with many different dependencies using the same set of libraries. But this can very easily be co-opted to put libraries anywhere, right? So the idea of address space layout randomization is, hey, when we start off the program, let's choose a random spot. Might be here, might be here, might be there, wherever, and we'll load libraries there. And then when, as an attacker, you hijack control flow and you want to return to libc, and you think you won, you return into some random place where nothing is at, and you're screwed because the program crashes. Because it's not actually running system, you just jump into an unmapped section of memory. And so this was a very effective defense technique for a very short amount of time. And there are a couple of reasons why. One of these reasons is that there's not, on a 32-bit system, for example, there's not that much wiggle room. where you can load libraries into memory. For one thing, you can't load libraries into the top half of memory that's reserved for the kernel. So right away, that's 1 bit of entropy less. You can only load libraries straight off the bat to the 31 bits of memory. There are other constraints. Generally speaking, you want some large set of data for the heap. You don't want it to interfere with the stack. Realistically speaking, libraries, depending on the implementation of ASLR and so forth, have anywhere, depending on the system, have anywhere from 8 to 19 bits of entropy where they can be placed. 8 is obviously trivial, right? That's 256 times you have to exploit something. This sort of 16 bits of entropy number that oftentimes gets thrown around, also easy, depending on, as long as your exploit runs in some reasonable amount of time, that's not like hours, you can even parallelize it, try multiple connections at once. It's no good. On the 64-bit platform, now we're talking, right? On 64-bit platform, there's much higher amount of entropy. I don't remember the exact number, but it's not something that you were able to enforce. Was there a hand with question? I must have hallucinated.
I do have a question about, is this truly random, as in is it across the distribution, like, do you use dev random or dev random or whatever to do that? Or?
I can't make a claim for where the randomness comes from, but it's not based on the startup time of process.
Okay.
It is a good pseudo-random source.
So it's pure. Okay.
Yeah. Of course, 64-bit architectures are much more secure. And then, while we're at it, we can, at least for example in Linux, we can randomize other things in memory, right? So libraries aren't easy to target, right? But the stack, think about the stack. Things on the stack are always addressed relatively because a function could be called from a number of contexts. You can't assume exactly where it is on the stack. So the stack can be randomized. Dynamic memory, the heap, right? You always allocate the heap. You don't make assumptions where it's going to be when you're writing code. The heap can be randomized. Almost everything can be randomized. And ASLR is enabled in Linux by default nowadays. This started happening probably around 2010, 2011, when a lot of these attacks, returning to libc and so forth, gained prominence. And I remember, who here is familiar with capture the flag competitions? Awesome, yeah. So Adam and I competed together on a team called Shellfish back in the day. And around 2011, ASLR was pretty widespread, but capture the flag competitions didn't really use it. It was considered too difficult to bypass. To the point where, at one point, we were hacking something and we realized that, hey, they have ASLR enabled. Holy shit, these guys are serious. And we messaged the organizers and said, hey, just so you know, you accidentally left ASLR enabled. Like, oh crap, thank you for reminding us. And then they turned ASLR on. So things have progressed quite a bit. ASLR is now enabled in default, by default and assumed to be present in every introductory hacking challenge and so forth. It can be turned off by writing a 0 to this kernel configuration parameter in /proc. It's implemented using this combination of support in the kernel and support in the Linux loader. So, the stack will be mapped in somewhere random by the kernel. The libraries are this kind of collaboration between the loader and the kernel. Specifically, when you memory map something, you can have it give you base address, and we'll jump back to this a bit later. When you map some memory in Linux, the base address starts out randomized for a process, and then it is offset from there. You can even randomize the location of your executable. This is called position-independent executable code. And nowadays, it is done by default, but this was not the case for a while. 32-bit platform just has some overhead because Mike mentioned it briefly later, but there's actually let's mention it briefly now. On 64-bit platforms, you can actually access here where we have, let's say, this call, right? Obviously, this can be done offset, but in 32-bit platforms, there's no support for accessing memory relative to an instruction pointer, right? So it's very hard to have global data in a program that is going to be moved around. You actually have to lose some performance overhead by devoting your register to always keeping around your location in memory. On 64-bit platforms, this is no longer the case, so ASLR is much more performant and is enabled by default. Of course, we'll cover what ROP is in a second, but the more things are randomized, the more resilient your process is to being exploited. So, how would we exploit? First of all, how do we, practice exploitation in the modern world where ASLR is enabled? As I mentioned, you can turn off ASLR for your whole system, or you can turn it off for one shell or for one process. So this command will disable ASLR in the sh that it runs, or any other command that you run with it. Sometimes, as I mentioned, you can defeat ASLR by brute forcing. If you can control how the process starts up, you can often screw up the amount of bits available for ASLR. You can, for example, using ulimit, Linux command to set process limits, you can set an insanely huge stack that will take up so much room that there won't be any room left for ASLR. But in the general case, you have to do a two-step attack. One, you have to leak an address through, format string, out of bound read, whatever attack, and then you do the hijack of the control flow to where you want. So if you can leak the address of libc, then conceptually you have the same attack as you were doing in GDB where you printed out system, and then you use that to and then you use that to jump the system. Or you can do something a little more interesting called return-oriented programming. Return-oriented programming is basically a generalization of the return to libc approach. And the idea here is, okay, return to libc allows us to execute library functions. But we don't need library functions. Library functions are for chumps. They're for programmers. They're not for hackers. Right? We can actually use little tiny pieces of library functions. If you have a function that does something, 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 and returns, you can actually jump here and do one little thing and return. And then do another little thing and return. And you can actually combine these like a sort of Frankenstein to carry out whatever we want to happen during exploitation. It was introduced a while back to work around these defenses. And it was generalized in a paper called The Geometry of Innocent Flesh on the Bone, which is a very kind of punk rock title here. This paper recently won the Test of Time award at CCS, or whatever the equivalent of the Test of Time award is there, because this paper basically said, hey, as long as you have enough code, by taking these little snippets and chaining them together in the same way that we saw that system will return somewhere after it's done. Right? By taking a bunch of these guys, you can do anything. We're omnipotent. So, let's see how this works. We have our old friend, the Monocle program, compiled now with even fewer protections, because now we're pretty major hackers. We want to carry out a return-oriented programming attack. The idea is, first we define gadgets in the binary. This little guy is called a gadget, a piece of a function ending in a control flow transfer that we can control that will do bit by bit what we want done, right? So, the essential idea is we find enough of these gadgets and we put them together in a way that our shellcode is now built from these little pieces of code in the program. And at the end, we want to call exec_ed, just like we did in our old style shellcode that ran on the stack. Right? And so what do we need to do that? We need 11 in EAX, the number of the system call for exec_ed. We need the address of bin_sh somewhere in EPX, right? The first argument of exec_ed. We need an argv set up in ECX, the second argument of exec_ed, and we need a null for an environment, or a pointer of a null for an environment that exists but is empty in the third argument to exec_ed. Cool? That makes sense to everybody? Perfect. So first question we're faced with is where to put bin_sh. Alright, well here we're going to assume that PIE is not enabled. So we're going to assume that this is our binary and that we know where at least the binary is in memory. Okay? We know where the binary is in memory, so now where do we want to put bin_sh? Well, there are some places that are writable, right? And one of these places is .data. So that's the global variables, the kind of fixed global variables of the program. It's writable. Base address is 80EA060, and it's pretty big. It's OXF20 in size. How big is this in decimal? Should be almost 4 kilobytes, right? Anyways, it's pretty big, so there's plenty to play with. So let's decide to write stuff there. So now we have where we want to write to. Now we need a gadget that will do a write. And again, we're not going to find a gadget. That's not quite true, but let's assume for now you're not going to find a gadget that will just do that on its own. So we need to build it out of little gadgets. And the first thing we need to figure out is, hey, how are we going to write bin_sh to memory? And so after a lot of searching, especially if you do it by hand, like we used to back in the old days, you find a little gadget. At 809A67D in the program, you have something that writes the value of EAX into EDX. Again, I apologize for this poor taste of assembly format, but that's out of my hands. And then you return. And if you do exploitation enough, you very quickly memorize C3 as a read. So you do this, and this gadget gives you the ability to write 4 bytes anywhere you want in memory as long as you control EDX and EAX. All right? Awesome. So then if basically we can put /bin right into EAX, that's 4 bytes, put the address of the data segment into EPX, well, EDX, that's wrong. That's okay, so we put the address of data into EDX, and then trigger that gadget, then awesome, we run /bin, and so we need a couple of gadgets to make this happen, right? So now we figured out the right, so that's, you know, this last step. The first two steps are still a little mysterious. You're not fully sure how you'll accomplish that. So first, let's figure out how to get data into EDX. Well, a good way to get data into something is to pop it on the stack, especially when you control the stack. And so we find a gadget that does pop, EDX, and read. There's C3 again. If you do this enough, this knowledge never really stays around. But 5A, that's a printable character. You start being able to see it in a hex dump. Most of the pop, some random register, is a single printable character that you end up seeing in your creams. So this gadget, of course, takes what's on the top, and they call it. Did someone just ask a question?
No, I thought you said seeing in your dreams, right?
Yeah, maybe your nightmares.
Yeah.
So, of course, the top of the stack in this crazy way of drawing is actually at the bottom. It makes a lot more sense that the top of the stack on the left. Not really, but you know. Anyways, moving on. So it takes what's on the top of the stack and puts it into EDX. And of course, Adam asks, how does this help us? But you know, it helps us because it gets us that much closer to actually writing this SH, right? So here we modify our payload generator. So this 0806E91A is pop EDX, and so let's see what happened when we actually run through it. We start out with okay. So we have here that's the pop EDX. We do a leave after we do the overflow. That puts us here at the ret. When we do the ret, we jump to pop EDX, and when pop EDX runs, it'll pop off this /bin into EDX. So look at the value of there's no value of EDX in here before now. Obviously there is a value, but it hasn't been put on here. So over here, EDX, after we pop it, boom, EDX has been SH. Awesome. Or sorry, bin. Okay? So that's this is the same as what was on the stack. So now by triggering a gadget that does pop EDX, we have now gained control of the value of EDX. And return-oriented programming is all about the slow battle to gain more and more and more control, right? Sometimes you have to do it bit by bit. Sometimes the only gadget available in your program is like increment EDX. It's actually very often true for EAX, for example. So if you have increment EDX and you want to set EDX to this value, it's hell, right? There are other things you can do around it, like, you know, maybe you can control ECX, and then you can somehow move that into EDX, or maybe you're able to trigger a multiply instruction, which actually puts some values in EDX implicitly, and so forth. Anyway, so then this returns, and we continue executing, and in this case, we will execute this what was over here as EDCB, and this was with this was without the slash. This was EDCB. So now EDX is EDCB, and when we return to this BFFFF, best friends forever address of the kind of old school location of the stack before it got randomized away. But you know, nowadays you don't see the stack at this point. So now we have control the value of EDX. And the point is we have the address of our gadget. Where's the everyone watch the dot? Alright, so add to our gadget, add to what it pops, add to where it returns to. Okay? Awesome. So, now we're just missing a data to, yeah?
I missed something. So you said the first step is kind of finding the addresses of these gadgets. How is that any easier than finding the addresses of, let's see, the randomization?
Because the addresses of these gadgets are in the binary itself.
Okay.
They're not in this.
Okay, got it.
So you can't, of course, expect the binary itself to have a function that says, oh, okay, you win, here's a shell. But of course, any binary that's sufficiently large is going to have a bunch of these little gadgets that actually do some useful stuff, some stuff that the program's supposed to do, but when you pull them all out and put them in together in the specific way, they allow you to achieve.
That's why you said with different programs, you have different things to work with.
Yes, exactly. And really, it depends on the size of the program. Realistically speaking, I forgot the exact, but you know, if a program is over 50 kilobytes and measures have to be taken to explicitly reduce the amount of gadgets in there, you will have gadgets to do anything you want. And there are actually many tools that will do all the searching for you automatically, build entire exploit chains automatically.
Cool, can you give us those names, please?
Huh?
Can you give us the names of those tools?
Yeah, absolutely. I might even demo it if you have time. Now we need a gadget to, so we have a gadget to get our data into EDX, you get whatever address, and now we need to get whatever we want to write into EAX, and it's the same sort of thing. There's another gadget at 80 E6, D6. I don't know, maybe this is a made-up address because I don't have the original binary. Presumably the binary compiled earlier today, it'll be somewhere else. And there's, you know, a gadget that'll do the exact same thing for EAX. There's one for EBX. There's one for ECX. We have quite a few things that we can work with. There's one to XOR EAX EX and EAX to 0. That's a very common thing you want to do. There's one that increments EAX. I think I even mentioned this pattern before, increment EAX read. And what you'll see as you look at more and more binaries is that there are gadgets that are very common. You can almost always, obviously, find pop EPP red, right? You can often find pop in 64-bit x86. You can find pop RSI, pop RDI red. Pretty reliable. And so there are these many of such gadgets that exist. Oftentimes, you can just find programs, gadgets that set AAX to some specific return value red, and this sort of thing. And of course, the ever important system call gadget, int 80, also somewhere on the stack. You guys know about system calls. Someone not. Awesome. All right. So now, let's say we have all these building blocks. We can build our shell code, and we go on to building the raw chain. And of course, we can continue doing this in this hacky-ass way, where we have to do the ending conversion ourselves and give us a big headache. But that's a pain in the ass. So let's actually use some real Python to make our lives a little simpler. Python ships standard, in the standard distribution of Python, you have a library called struct. It does a lot of structured packing and unpacking, and one of the things it does is it allows you to take an integer and display it, convert it to a little endian. So this less than capital I means create a little endian, unsigned 32-bit integer, or pack an unsigned 32-bit integer into a little endian. So basically, here's our payload. We start out with our buffer and some garbage value for our frame pointer. And then we say, okay, let's copy bin to the string /bin into the data segment, okay? And first we jump to this pop EDX return. Then what it goes into EDX. EDX will be the address of our data segment where you want to write to. Then it'll return, and where does it return? It'll return into the gadget pop EAX and return, and that will pop /bin into EAX. And where do we want to have that return to? Our memory run gadget, which writes the contents of EAX into that address pointed by EDX. And after this ROP payload runs, we will have the string /bin written into the data segment of the program.
So do we care what's in those memory locations prior to that, or does it not matter?
Usually, by the time you're doing this, you fucked up the program to the point where it's no longer doing its original operation, right? And so it likely won't touch those again. Now, sometimes you have to do an exploit stealthily so that the program can keep running after you're done. Then you care. And sometimes, if you have a multiple shot exploit, so you get some in some very complex stuff, you get some raw payload which are at a low privilege level, and you need to set up something and then let the program run for a while and then exploit it again later. Then you do care and you don't want to clobber what's there. In that case, so this /data, okay, that's going a little too slow. In that /data, or the .data segment, you have almost 4 kilobytes, right? It's unlikely that they're all used. There's a lot of padding between variables. Oftentimes, you map an entire page of writable memory, because you can't map less than a page, but you only use a little bit of it. And so usually there's stuff that you can write to that won't matter. In this case, just for the example, we're using .data. So, of course, it's not just /bin we want /bin /sh. Presumably, a couple classes ago, you covered this whole thing where, since you're using string copy to write over the stack, you need to avoid null bytes. Does this sound familiar? Cool. And so yeah, you use //sh. So now we pack the same thing, but you do, instead of this data address, you do data +4, and you write /sh into it. Boom. And we call the same, you'll trigger the same gadget for that. And then you do want to null terminate the path so that system will, or whatever, execv will read it properly. And so we do the exact same thing again, data +8 this time. But here we do XOR EAX rec, a different gadget that doesn't take any data as input, doesn't pop anything off the stack, but zeroes out EAX, and then you do that right. Okay, so now we have in memory bin sh, and then so now we have the first argument to execv. Now the next we can build up the argv vector, that second argument. So we need to push a bunch of pointers to the stack, and it's the same sort of thing. You pick an address for this vector, and we use our same set of our same memory write pattern, write the .data +12. So we can actually write this out to keep track. So if we have our .data memory here, that's not enough. Let's do. That's not much better. Anyways, all right. So let's say here's .data. After this, what will this look like?
It'll be written to the right with our shell code, essentially, that is the instructions, right, that we put in there.
Well, after this executes, when we have the exploitation, after all of these memory write gadgets run, this will write into the data segment /bin//sh, and then 4 zeros, right? And then we want to write a bunch of, write this vector for exec_v. So what we want to write is, so this is, this is 4 bytes, this is 4 bytes, this is 4 bytes. Now we want to write a pointer that, right, so into data plus 12, so this is data, data plus 4, data plus 8, data plus 12. We want to write the address of data, a pointer into /bin, right? Because if you remember, is this in racetrack? Ooh, that's nice for me. You remember exec_v, you need to run exec_v, our command. A list or a array of our R&D array. Depending on the specific shell that you're running, you can leave this completely blank. So you can just give a pointer to a null byte here. But let's assume they're nicer than that. So we probably want to do give it an RB0, an RB1, or sorry, an RB0 and then a null byte. This is a null terminated array. And then we want to give it a null byte for the environment, or pointer to a null byte. It's the same thing for the purposes of that. It's either a completely non-existent environment or an empty environment. And so here we are building this, right? We're getting an address to the that data, which is going to point right here, and we are writing it here, right? So this now points to that to /bin/sh, and so that's this pointer, the 0th argument to the argv to exec_v, and then we add a null byte, and so here we want to write a null to here. So again, this is 0, 0, 0, 0. And so now when we call exec_v, the arguments we can take and give it are this guy, and then comma a pointer to this guy, and this has, oops, sorry, a pointer to this guy, and this has a pointer to the string and our null. Okay? Cool. And then now we have all the data in memory that we need, and it's time to actually make that call. So what do we do? We need to do this exec_v.data, that first arrow, data plus 12, the second arrow, and it looks like Adam wants to be clean, and instead of a non-existent environment, do a blank environment. Does everyone understand the difference here between passing a null and a pointer to a null? So the environment is an array of strings, array of pointers to string, right? And if you and the environment and our V array, they're both null terminated arrays. So it'll keep reading until it hits the null. Right? In this case, this is a null terminated array with one element. Right? So it has a pointer and then null. This, if you have a pointer to a null, it's a null terminated array with 0 elements. It's a blank environment. If you just have a null, it's just no environment, which the kernel treats the exact same way as a blank environment. It's just kind of a distinction without much of a difference. Cool? Cool. So, EDX is the first argument to exec V. That's the path. So we have a pop EDX gadget that we found earlier. We use it with data as address. Now we control EDX. The second argument is ECX. That is the pointer to this list, which is we want to point to EDX plus 12. So again, we found a pop ECX object gadget. We do this. We give the address of data plus 12. And EDX is the third one, and that's to the environment. So we have an EDX gadget as well. We're very lucky right now. This is like Christmas. And then we give it this plus 8, which is the address of these nulls. Cool? And then EAX must be 11 in order to trigger exactly the system call. And so if we are unsure that EAX is 0, we want to zero out EAX, of course. This is X over EAX. And then we increment it 11 times. Why did we not just set it to 11? Why did we do pop EAX red and then put 11 in there?
Would that have included,
It would have included something.
null bytes?
It would have included null bytes in our payload here, which would have caused stir copy to terminate copying, and it would have screwed up our exploit. So then we trigger the actual system call, which is here. We have a gadget for it. We don't need it to return. It doesn't matter what it does afterwards because we'll have our shell. And then we just print the payload out and pipe that into the program. So let's see what happens when we run it. And let's break at this 48E67, which is, honestly, I don't know what it is in this program. But we'll see in the slide. So we break at this 804.8E67. We run the exploit. Let's see what happens. So here is our ret after the overflow, after we trigger the buffer overflow and do a return. Right? This is our state of our register file. That's the state of our stack. And let's see. So we hit return, and we begin our payload by popping at this 91A. 91A, that's where we return to from main. And that's pop EDX. Here you're building this bin SH. That's the address of that data. We pop it. Now it's an EDX. Then we return to this pop EAX. And here we've written out our gadgets concatenated as a return-oriented program. Right? All of these rets, they just transfer control flow to the next gadget. These aren't contiguous in memory, right? They're just contiguous in terms of how we execute right now with the following stack. And so we got EDX into the register. We set the prompt value of EDX. Now we're going to set the prompt value of EAX. Now we're going to do the write over here of EAX into EDX. And then we're going to return. So now we've written this part. This is awesome. We've written it. Check. Now we go back to pop EDX, right? To write the second part, that SH. Cool. We pop EDX again. So now this is .data plus 4. Return into the pop RAX, and so now our EAX. Do I keep saying RAX, RDX? No. Okay. So you guys know 64-bit x86? Did I cover it? A little bit? Cool. Yeah, so EAX in 32-bit is the equivalent register in 64-bit x86 is RAX. I work mostly in 64-bit stuff, because most things now are 64-bit. It's a synonym, let's say. Anyway, you pop EAX, and you pop EAX in your return, so this is now // sh, and we keep going. We just went through this whole thing, what it's going to do, right? So now we set up an sh. Now we're going to set up this null bytes, this EAX plus 8, this guy. You do XOR EAX, and now EAX is 0, and we return from there, which goes straight into our memory write. Boom, now we've written this. So now this check, this check, this check. And we need to write 2 more things. Of course, we set EDX to 6C, which is data plus 12. Run it, boom. Set EAX to .data to make this pointer. Boom. Run it. Now we set EDX to here to write this null byte. EDX is set to that plus ORS10. XOR EAX to write it 0. Boom, write it. Now this is done. So we're done with the memory part. What are we doing now? We're setting up the call frame of the call site of the system call. So you pop EBX, so EBX is pointing to that data. Pop ECX, ECX is pointing to our list. And we pop EDX. EDX is, where did EDX go? Oh yeah, there we go. EDX is pointing to a null byte. XOR EAX. EAX is now 0. We increment it a bunch of times. Whoops. Until it's OXB. And then we trigger the system call and we live. So, before we trigger the system call, let's look at the state of memory. So if we read out .data, you'll see that it says bin.sh. If you read out a bunch of words from here, you see that we have a pointer here to .data and then a null byte, or a null word. And then, if you read out the string, if you read out the word here, you also see a null word, right? So it's all set up. I've convinced you by showing you text popping up on the slide that we're about to exploit this thing. We hit continue and boom, it says continuing and boom. We have a new program, bin dash, which is the minimalistic shell nowadays in most distributions. That's what we ran. And we have an ASLR proof payload, kind of, as long as your binary is not position independent. And binaries nowadays are position independent. So, how do we get around that? I'll give you guys a couple of ideas. One is sometimes you can leak you can leak an address. Maybe you can't leak an address in libc, but you can leak an address in libmath for some reason. Or lib weird fucked up library, right? The way that ASLR works in Linux is that, oh hey, we have a whole unused board, this is awesome. Okay, the way ASLR works in Linux is you have your amazing memory layout that's horizontal. Somewhere in here you have your program. Maybe you don't know where it is. Its position is independent. Somewhere you have a stack. Somewhere you have your heap. You don't know where any of this crap is. And then you have libc. You don't know where that is. And notice that I drew them next to each other before. That's not an accident. Linux will always map them next to each other, which is really stupid. Because if you leak any address anywhere here from any of them, you've broken library ASLR. You know where all the libraries are. So that's one way to do it. You don't have to even necessarily leave the address, the exact address you need. You leave almost any address. Usually when you leave an address, from there, you know enough to break stuff. If you leave an address in the stack, then you know enough to mess up the local function frames of a lot of other functions and so forth, and try to, like I said, this sort of modern implementation is always this battle of getting a little more control until you've exploited the program. If you leave an address in some other library, then you're pretty much good to go with a follow-up exploitation and so on. Another way that ASLR suffers nowadays, and this is kind of the emerging technique, is that I mentioned position EAP relative addressing, right? So in modern, like in 64-bit x86, you can do memory addresses, and the compiler does do them based on the instruction form, right? And so somewhere you might have a thing that says move RIP plus EBX, or let's not use EBX, but it's going to RIP plus ESI into EAX, and then jump, or whatever, do something to EAX, right? If you control ESI is this memory access is an offset from ESI. So it doesn't matter that you don't know where the program is. If you control ESI, and the program is here, and you set ESI to 10, you will do a memory access into the program, into a valid address space. That means essentially that it is not impossible, that you're not seeing this a ton yet, but it's not impossible that ASLR isn't necessarily powerless in the face of complete position-independent code, but it's less effective, or it can still be done in some sort of a position-independent, or RUT isn't powerless, but it can still be done as some sort of position-independent RUT, maybe. That's an emerging sort of thought. Anyway, there's a lot of tooling for doing this automatically. Let's see about blowing the rest of the class on a demo. Oh, we are done? Ooh, bummer. All right, next class, ask Adam to show you guys AIMROP. It's a tool that came out of our research lab in my graduate studies. AIMROP. I will write it somewhere. AIMROP. Look at that. It's not turnkey. It's not easy to use. This might be a little easier to use, but it's less general. So AIMROP is a tool that will analyze a binary and will automatically synthesize drop tables like this. As I said, it's not very easy to use. Cool. All right. Thank you very much. Yeah. And be sure to tell Adam about the correct layout of memory.